when we're in the rational functions, we're in the hairy edge of calculus. When we start talking about some of the stuff we're going to talk about, without using we call it, the mathematics way, we call it hand waving, is that we'll talk about this stuff, but we won't actually put the calculus notation behind it, as you would in a calculus class. But it is kind of some calculus ideas. And a rational function really is a polynomial divided by a polynomial. And essentially what we're looking at, rational always means fractional. So for us in this class right now, our rational functions will be polynomials over polynomials. You can have any function in the numerator, any function in the denominator, and it still would be a rational function. But the ones we study are just polynomials divided by polynomials, which is why we had the little quiz this morning that dealt with the whole idea of a polynomial, the degree of a polynomial, the power function, because all of that's going to come into play because a rational function is a polynomial divided by a polynomial. And of course we know for sure that q of x, the denominator, can't be 0. It has a domain issue. So the denominator can't be 0, never ever, never ever, never ever. So it's got a domain issue. So that's the first thing we investigate. We define it, and we define it to be a polynomial divided by a polynomial in this chapter. Once we define it, then we're going to look at the domain of it, and then of course then we're going to be looking at some of its characteristics that's going to come along with it that makes it different than the functions that we have studied before. So of course, if we're going to find the domain of the function, we know that the denominator can't be 0, which says that 3x squared plus 5x minus 2 can't be 0, and we're back to factoring, which is 3x and x, 2 and 1, plus and minus. So this says that x can't be 1/3, x can't be -2. It can be anything other than those two. Yes? Oh, yeah, okay, thank you. It can be anything other than those two. This produces something. These exclusions will now have meaning, because these exclusions produce something that we call the vertical asymptote. Now, as a student, I really did hate asymptotes. And why? Because I really, in a sense, did not fully understand them. So I really kind of hated them. And that says, well, what happens with 1/3 and -2? What does that mean? Now remember, we've always said one thing. Division by 0 is undefined.
Sorry.
Oh. In our other classroom, we have computers all the way around the room, and all of a sudden they turn themselves on, and we hear these noises. So I'm kind of thinking, yeah, well, yeah, they're going over there. So undefined. Now, what's that going to mean to us? It does mean something. What it means is something along this line. If I look at 1 over x squared, I know that the domain is all real numbers. X can't be 0. Now look what happens at x equals 0. At x equals 0, if I'm coming in from the left, this guy is going up, never crosses the x-axis, but is moving in toward the x-axis. So essentially what would happen is this. As x goes to 0, I'm going to use that little arrow that means goes to. As x goes to 0, y goes to infinity. It just keeps going. Undefined, plus or minus infinity in this instance. So if x goes to 0, and I'm coming in, x is coming in and getting closer and closer to 0. So x is going to 0, and I notice that y is going up. Y is going to infinity. The closer I get to 0, the bigger y gets. And if you really want to take a look at the table that would generate that picture, here's the table. I'm coming in from -1 and getting closer and closer to 0. Notice what the y values are doing. I start at 1, 4, 100, 1,000, and this is a million, and I'm only at 0.001, negative. The y values are getting very, very big, very fast. We would say at 0 it is undefined, because 1 over 0 squared is undefined. But the closer I get to 0, the bigger the y values are getting. Now, if I'm coming in from 1 on the other side, you notice you have the same thing happening. 1, 4, 100, 1,000, a million. The y values keep getting bigger and bigger and bigger and bigger. And we're looking at, in this case, a thousandth. A thousandth is not a really small number. If I had 1 and 50, if I had a point, 50 zeros and a 1, that's a very small number, but y would be so big that my calculator probably wouldn't be able to handle it. So what you're looking at here is a vertical asymptote. As x goes to 0, y is going to infinity. They also could go to minus infinity. And what a vertical asymptote really is, it's caused by a division by 0. That's the cause. But from a practical point of view, a vertical asymptote, and I'm going to call it a VA, a vertical asymptote is a wall that the graph never crosses. It's like looking at that wall. Now, unless you're one of the X-Men, and I think it was a shadow cat that can walk through walls. So unless you're one of the X-Men, you're not going to go through that wall. You may find a way around it. In other words, you would walk along it to see if there was an opening, but you're not going to be able to go through it. And that's what a vertical asymptote is. It is a wall that the graph never, ever crosses. It can't cross. So instead of, if you were walking toward that wall, you'd have a choice. You can either put your nose against the wall and not go any further, or you're going to say, I'm going to curve either one direction along the wall, or I'm going to curve another direction along the wall. And that's what the vertical asymptote forces. It forces the graph, when it comes in toward the wall, to basically bend. And it'll either bend up the wall or it'll bend down the wall, depending upon what the function is. But it will never, ever cross the wall. So what vertical asymptotes are, they're caused by a division by 0. That's that old, I can't divide by 0, because it's division by 0 is undefined. It's caused by a division by 0. It creates a wall that the graph will never cross.